All right, let's talk about repeated measures, ANOVA. All right, repeated measures, why do we use it? What is it? Again, we're using the same participants, repeated measures, repeating the participants in many conditions of an experiment. So why do we use repeated measures versus a regular ANOVA? Well, we need to reduce the unsystematic variation so that we can have the analysis be more sensitive to the experimental effects. It gives us a little bit of good news. We don't have to have nearly as many participants, but when we do use the same participants over and over again, they could have fatigue or they could have learned behaviors. If you're using hard data, such as maybe you're testing the pavement over and over and over again, there's still fatigue that's associated with that pavement from one test to the next test. All right, so repeated measures, again, same participants in all conditions of an experiment. We cannot use the traditional ANOVA because obviously we're violating independent data. The data is no longer independent, it's dependent. Again, independent data taken under different experimental conditions. Here we have related data because they are the same participants. So it's very similar to a multiple paired t-test, whereas the traditional ANOVA is simply a multiple t-test, student's t-test. So that is what's nice about the repeated measures, is really just a multiple paired t-test. All right, we have some assumptions. We have veracity, which the relationship of the pairs between the conditions is similar. It's something similar to compound symmetry, but we have talked about it before as more of homogeneous variances. So the variances across the conditions are equal, and the covariances are also equal. So that's what we call veracity. Not wholly recommended for repeated measures, but it will be more for the mixed design, as well as a little bit for the repeated measures. We just want to make sure that we have equal variances between the different treatment levels. We need 3 conditions for it to be a problem. So if it's a problem, we're going to have variance A and B, variance A and C, and variance B and C fairly equal to each other. So that means we have local severity, circularity, 2 of those are identical. But veracity, in general, we have to have most of those things happening. All 3 of those things have to happen. All 3 of those have to be equal. So we're probably not going to run into veracity very often. How do we test it? It's called the Maluki's test. If obviously our p-value is less than 5, we have a violation of it. The F ratio is going to be different. We cannot necessarily use it straightforward. It's also dependent upon the sample size. The very large samples mean small deviations can be significant, and we can also lose power with it. Obviously, if it's greater than 0.05 at a 95% level of confidence, we do meet veracity. So there's a number of corrections that we can apply to the F ratio, which SPSS actually does for us. The first one that we're actually going to be using is a greenhouse geyser estimate. The closer it is to 1, the more homogeneous the variances are. So you can evaluate how close they are by just looking at the greenhouse geyser. And there's the other estimate, which we really aren't going to be using. Just a greenhouse geyser gives us that element to be able to examine how close they are, and the other estimates simply do not. All right, what if you do totally violate veracity? You can multiply your degrees of freedom by those greenhouse geysers to correct the effect of veracity. You probably aren't going to be running into that too many times. If you've got real severe violations, you might have to use the ANOVA or the MANOVA, which is the multiple analysis of variance. All right, let's look at the repeated measures. Everything else that we've talked about for ANOVA has really been running underneath the sum of squares between participants. But because this is a repeated measures, we're going to be looking at the sum of squares within individuals and then drawing off our SSM and our SSR, the model sum of squares and residual sum of squares, based upon the within. So we have that difference with the ANOVA is where the sum of squares are coming from. So let's look at an example. We have, are certain fast food restaurant foods more revolting than others? We're going to look at McDonald's, Wendy's, Burger King, and Taco Bell. And our dependent variable is the time to a stomachache. So we're using the same people, right? 8 people are going to taste all of these and the time to a stomachache. So with repeated measures, when we pull that up, we're not going to go through SPSS for this because it's just another ANOVA. Everything is pretty much the same with the exception of this piece. So what we have to do, we're going to have to add restaurant here. So you would type in the factor name and how many levels, and then you hit the add, and then it will show up as such. And then we have to hit the word or the button define. After we hit the button define, this is what we're going to see. 1, 2, 3, 4. So we're going to have to say that McDonald's, you'll take McDonald's and you hit the arrow into 1. Wendy's is 2, Taco Bell is 3, and Burger King is 4. That's the exact same way that we would do it if it's done the exact same way it's coded in SPSS. So you have to make sure that the numbers do correlate directly with how it's coded in SPSS. Then we can run some contrast. Contrast here should be repeated because we are using multiple same subjects. So use repeated, hit the word change, and we should see it show up there. But the bad thing about repeated is you can't specify last or first. So the computer is going to make those decisions. Post hoc test, there's some complications because of veracity. And when you pull up the post hoc, you see that you can't do anything here. It's blank. If you ignore your complications, you can use the Bonferroni. If you don't violate veracity, you can use the Tukey. But they can't be done in this screen. You're going to have to pull up the options screen. And here you can move restaurant over. And when you pull this down, you either have the option of Bonferroni or Tukey. Go ahead and select Bonferroni. Don't forget to compare the main effects. And also ask for descriptive statistics. And after that, we're going to get our descriptive statistics. So again, our output is time in hours to a stomach ache. So it looks like for McDonald's, you had an 8 hours time to a stomach ache. Taco Bell and Wendy's were just above 4, and Burger King was just above 5, almost to 6. So again, this is useful if we're interpreting the effects that will come from the analysis. All right, next step is to look at this veracity. We have a problem with this one. We have a significance value that is less than 0.05. So we have violated we have violated the assumption of veracity. All right, so now we want to know, we have to look at the greenhouse geyser. And I said the closer it is to 1, or the closer it is to the lower bound, there's the 2 ways we can look at this. I didn't talk about the lower bound before, but we're going to talk about the lower bound here. So what I had said before, the closer it's to 1, the more homogeneous the variance is. So we're at 0.553. So it doesn't seem that we're really too homogeneous. So then we can say the greenhouse geyser is not close to 1. But we also would like it to be close to the lower bound. All right, so because it's not close to 1, the data is probably not really spherical. And because it's closer to the lower bound, that is also telling us we probably have some substantial deviations from sphericity. So we want it to be as close to this value as we can, because that's good. And we want it to be as far away from 1 as possible. So we're going to go forward and proceed with the test, because we don't think we have severe violations of sphericity. All right, so our main Anova output, we see that we have an SSM of 83.125. And our degrees of freedom is 3, because we're going to assume sphericity. And we have an SSR of 153.375. And we have degrees of freedom there of 21. So our F value is simply our MSM 27.708 divided by our 7.304, sorry about that, which gives us an F value of 3.794. And we have a significant difference. So the mean value of McDonald's is not equal to the mean value of Taco Bell, which is not equal to the mean value of Wendy's, which is not equal to the mean value of Burger King. So we just know that the means are not equal, but we want to know which is which. All right, so let's look at this again. The sphericity, because we do violate sphericity, it makes our F ratio inaccurate. So when you look at the F's are actually all the same. So if you had a significant difference in sphericity, this is how you would go through this process. The F value is the same. The only difference that we have between the assumption and the non-assumption is the number of degrees of freedom. So all they essentially did they had our greenhouse geyser was 5.33. If you take the number 3, which is our degrees of freedom, and multiply that, you get the 1.599. So that's how they came up with the degrees of freedom factor. So, and then they did the same thing. 21 times 0.533 gives us the 11.190. So that's where they came up with those values. So if we're going to look at this table, the greenhouse geyser is somewhat conservative. It actually accepts the null. It says there's no difference between restaurants. And the other value is a little bit more liberal. It's rejecting the null. So now what do? You have 2 estimates that you use to correct the assumption of sphericity, and they're different. Now I said we're going to generally use the greenhouse geyser, but we should also look at the secondary one because we want those 2 values to produce the same result. All right, what do you do if they are not having the same result, which is what we have here? Let's take the average of them. All right, so now we end up with 0.055. So what we should do here is just conclude that the F ratio is not significant and accept the null. So the reason we did this is because these are so different. They produce opposite results. One is conservative, one is liberal. We want to find somewhere in the middle. This is our midpoint, and we're still going to accept our null. So let's go ahead and continue on with that assumption of sphericity because we want to know the true answer. What this is telling us is that we do have a significant difference in restaurants. So this is just a multivariate test. We're looking at all of the different references, all the different restaurants, and we have significant differences across each. Now, as a matter of, which one of these do you use? Again, sometimes it's just nice to take the average of all of them and proceed forward. Now, the contrast in the post-hoc test, obviously you have to ignore if the main test is not significant. So we're going to proceed even though we know that based on our analysis we should probably accept the null because we did have some ferocity issues and we had to use the greenhouse geyser. But if we didn't, this is how we would proceed. So now it looks like this is our computer designed contrast. So level 1 versus level 2. So who is in level 1? It's McDonald's versus Wendy's. So level 1, we end up with a significant difference between McDonald's and Wendy's. Now we have to look at our descriptive statistics to tell us what that is. So we can say stomach aches arrive later after eating McDonald's than Wendy's. All right, then we can look at level 2 versus level 3. Level 2 versus level 3 is Wendy's versus Taco Bell. There is no significant difference. And level 3 versus level 4 is Taco Bell versus Burger King, and there's no significant difference. All right, how about our post-hoc test? Again, you have to know what 1, 2, 3, and 4 are to be able to figure this out. But again, you can use contrast or post-hoc test. If you didn't have any assumption, you would use your post-hoc test. If you had some assumption, you can use your contrast, but you cannot use both. You can only use one. So here, 1 versus 2 is a significant difference. 1 versus 3 is a significant difference. This actually tells us more information because it's comparing more restaurants against each other. It's comparing all of them against each other. So we just know that 1 is different than 2 and 3, but 2 and 3 are the same. So it looks like McDonald's does produce less of a stomach ache than 2 of those restaurants. What are those 2 restaurants? Well, 1 is McDonald's, 2 is Burger King, and 3 is Wendy's. So it looks like McDonald's is better than Burger King, and McDonald's is better than Wendy's. Sorry, Erica. Effect sizes. How to calculate the effect size, because we need this information to be able to tell whether it's practically significant or not. So this is just how we go through our effect size. McDonald's versus Wendy's is significantly and practically different. Wendy's versus Taco Bell is not, and we have a moderate impact for Taco Bell versus Burger King, so it's somewhat practically significant. And that's pretty much it for the repeated method.